I want to talk about the exponent rules. We're talking about exponents, and there are a lot of different rules that a lot of people find hard to memorize. I don't like to memorize anything in math. You really don't need to memorize anything. Uh, if you think about the definitions of exponents and what they mean, you can really look at the properties of exponents and figure out the rules without having to memorize them. That's what we want to do today. First, things we need to really think about are the definitions in terms of exponents. If I look at an exponential expression like 7 to the 4th power, we call 4 the exponent and we call 7 the base. So in the first line here, I have a base of 2 and an exponent of 5. And that means I multiply 5 2's together. 2 to the 3rd power, which means I have an exponent of 3. When we say, I can either say 2 with an exponent of 3, or I can say 2 to the 3rd power, or 2 to the 3rd. 2 to the 3rd power is 3 2's multiplied together. And 2 to the 8th is 8 2's multiplied together. You can do those on your calculator and see what the answers are, but in terms of the exponent rules, we're really more concerned about not the answers, but what the exponents and the bases mean. So the first exponent rule is, for instance, where we have 2 to the 5th power times 2 to the 3rd power. We're multiplying exponential expressions with the same base. That, if we look at what that actually means, that means multiply 5 2's together. I'm using the dot for multiplication. A lot of people get overwhelmed by the parentheses. So for these demonstrations, I use the dot. We don't use the X because in college we use X for other things. I've multiplied 5 2's together, and I'm going to multiply that by 3 2's that are multiplied together. And when I do that, you see all of a sudden that I have 8 2's multiplied together. So 2 to the 5th times 2 to the 3rd is 2 to the 8th. And if I think about what really happened, I wrote 5 2's, and then I wrote 3 more 2's. So I had 2 to the 5. I got my 8 by writing 5 2's and then 3 more 2's. So I got that 8 by doing 5 and 3 more, or 5 plus 3. So 2 to the 5th power times 2 to the 3rd power is 2 to the 5 plus 3 power, or 8th power. So in this case, I can add my exponents. If I look at the case of dividing dividing exponential expressions. Dividing exponential expressions, basically 4, 5, 6, 7, 8. I'll go back in and add my dots. Using the dots for multiplication instead of the X, because we use the X for something else. I could use parentheses as we've done before, but that gets kind of confusing for a lot of people. And dots work just as well. So if I take my exponential expression, 2 to the 8th power divided by 2 to the 5th power, or my quotient of exponential expressions, I can rewrite it as 8 2's multiplied together divided by 5 2's multiplied together. When I divide by a 2, I undo one of the multiplications. So if I multiply 8 2's, I divide by a 2, I divide by 2 2's, I divide by 3 2's, I divide by 4 2's, I divide by 5 2's, I end up with 2 to the third power. And if we look at our calculator, I will do 2 to the 8th power, and then divide by 2 to the 5th power. And hopefully you all realize that 2 to the third power, 2 times 2 times 2 is 8. So if I do 2, and this button here, the xy, x with an exponent of y, I do that, and then I put 8. And you notice up here I have 2, a little caret. Hopefully you can see that. You may need to zoom in on your screens. But the caret is the upside down angle. You will see that. A lot of you have the graphing calculators. The graphing calculators use that. Some other scientific calculators do not use the caret. They can actually show a number that's up above the others. You can actually see the exponent. But this calculator uses the caret. So 2 to the 8th power is 256. I'm going to store that in memory. And I'm going to say now 2 to the 5th power is 32. So I'm going to bring the 256 back from memory and divide by 32, and I do get 8. So 2 to the 8th power divided by 2 to the 5th power is actually 2 to the 3rd power. So I can summarize that by saying 2 to the 8th power, I wrote 8 2's, and then I ended up taking away 5 of those 2's. So I was left with 2 to the 3rd power. When we divide exponential expressions with the same base, we can subtract the exponents. The third situation that we run into, sometimes we have an exponential expression that is raised to another exponential, or raised to another exponent. So here I have 2 to the 5th power, 3, 4, 5. And I need to multiply 3 of those together. So 2, 2, 2, 2, 2. So I have 5 2's multiplied together, 5 2's multiplied together. And I'm going to have a third group of 5 2's multiplied together. And I'm going to multiply each of those together. So in the end, I really have 2 to the 15th power. Because I have multiplied 2, multiplied 5 2's, there are 3 groups of 5 2's. 3 groups of 5 gives me 15. So when I have 2 to the 5 to the 3rd, I actually have 2 to the 5 times 3, or 2 to the 15th power. A lesser used exponent rule, but nonetheless one that comes up is when we have the same exponent but different bases. So if I have 2 to the third power times 2 to the fourth power, that says multiply 3 2's together, multiply 3 4's together, and then multiply the two of them together. I could also actually do that with multiplication. Um, we find that we can multiply, we have a lot of things to multiply, we can multiply them in any order. The order we multiply doesn't matter. Our order of operations, say, is if we're going left, if we're only doing multiplication, we go left to right. The commutative property, or in this case, actually the associative property, says we can multiply different things. We don't have to multiply them in the order. If it's all multiplication, we can multiply in any order we want. And I want to multiply in this order because now I have 2 times 4 times 2 times 4 times 2 times 4, which is 8 times 8 times 8. So if I have 2 to the third power times 2 to the fourth power, that ends up being 2 times 4 to the third power, or 8 to the third power. So if the exponents are the same, the bases are different. I can multiply the bases and end up with one exponential expression. Bases are the same, exponents are different. We add the exponents. Exponents are the same, bases are different. We multiply the bases. Because the bases are things that are really being multiplied. So I continue to multiply in this case. With the exponents, exponents are just the number of times we multiply. So if I go back to my the case where I have the same base, different exponents, the 5 and the 3 don't represent multiplication. I'm not multiplying the 5 and the 3. They represent the number of times that we multiply something else. That's why the exponents end up being added, even though we're multiplying the bases.